unique character, Sam.
Thank you.
Very sure of himself.
He always was.
This is the first time I've ever seen you off balance.
I wasn't aware of it.
I was.
It came as a shock.
Yes, it did. To me, too. Sam will never tell. I'll never forget you saying that.
What makes you think he will?
What makes you think he won't?
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Dr. Alex Ivanko, who is the co-founder and CEO of HyPoint. Welcome to the show today.
Hello, everybody.
Okay. So you were educated at Saratov State Technical University in electrochemistry, right? So I'm curious to know how, I know that generally, I think when it comes to mathematics, engineering, Russia has some of the best educational systems, but I'm curious to know how your experience throughout your undergrad to your PhD program has prepared you for this particular startup that you're leading now.
So, because my general education was about engineering science, and the last course I made a decision to focus on electrochemistry because my coach, my professor, he recommends me to do so because he believed in some kind of future revolution, not only in hydrogen fuel cells, but also in lithium batteries and so on. So that is why I made a decision to switch from engineering science to electrochemistry. And actually, I think I won this game.
Well, I'm so glad that you made that switch. So speaking of, let's talk about hydrogen fuel cell. How is hydrogen fuel cell different from kind of the traditional fuel sources that are out there?
So hydrogen fuel cells, it's an electrochemical source of energy and source of power and electricity. So when you are not directly burn your fuel and electrochemically burn. So you should, in hydrogen fuel cells, for instance, hydrogen, divided to electrons and protons, and electrons go to the electrical load, and protons go through the special membrane, where that proton met with electron and oxygen we are breathing right now. So it's one more electrochemical reaction, and one of molecule of water usually is appeared. So, and if in comparison with and this electrochemical reaction is very efficient, so you can achieve efficiency more than 50% is not a big deal for any electrochemical power source. But in comparison with standard, like say, combustion engine, so their efficiency is very, very low, so not more than 20-25%. So, and this, when you are use hydrogen, not only hydrogen, I mean standard fuel as a fuel, so you directly burn that fuel in the combustion engine. This is a big difference.
So we're going to come back to this notion of efficiency and also some of your core IP around cooling as well. So we'll come back to that. But for the purposes of the listeners who are maybe not as familiar with kind of broad, term around hydrogen, can you talk about, when we talk about hydrogen in the context of renewable energy, maybe the different colors like green, blue, black, and what does each of those colors mean?
So actually, the colors of hydrogen is not like a standard. So it's just imagine that to easy to understand what is the main source of manufacturing and producing generation of hydrogen. So actually, if you are talking about the standards of industry, there are no any colors inside the hydrogen. So blue hydrogen usually goes if you were talking about hydrogen when we generate from natural gas. So it's a direct it's a direct transformation from natural gas to hydrogen. It's a very easy and one stage reaction, and it's very, very cheap. So that is why, for instance, you can see a lot of hydrogen right now everywhere. So it's like a blue hydrogen. Green hydrogen, usually, if we are talking about, but blue hydrogen contains a lot of CO2. So there is a not a lot of greenhouse gas emissions is generated through that reaction. If I'm talking about zero emission hydrogen, it's usually called green hydrogen, and it's generated from renewable energy sources like solar or wind power. So when you use you take that energy and way to electrolyzer, and this electrolyzer use water and generate hydrogen and oxygen. Yeah, so this is a green hydrogen, and this is right now the main concept for zero CO2 emission aviation, because you know that if you are using hydrogen in aviation or any transport, the main reaction will be only water. It looks like a zero CO2 emission, but we also should consider what kind of hydrogen do you use in your transport. So that is why absolutely carbon-free, zero CO2 emission application and usage if you also use green hydrogen in that chain.
All right, so that actually brings us to really the topic at hand, which is what is HyPoint and what are you doing within the hydrogen fuel cells?
So we are manufacturer of hydrogen fuel cells. So we are not manufacturer of hydrogen or aircrafts. So we are building next generation hydrogen fuel cell system with game-changing energy performance, specifically for air transportation needs. So we found a solution how to combine in the one system high specific power and high energy density, which is the main two parameters for aircraft designers, and they are really looking for such solution.
Okay, so again, just to kind of help baseline for those that are listening, is that a couple of areas that I think it's critical just to reinforce is this notion of aviation that's zero emission, and unlike lithium ion or other types of batteries that are out there, we're talking longer range in terms of usability, right?
Lithium batteries, of course, is also zero CO2 but it depends what kind of electricity this battery storage. So if that's generated from coal, electric power stations, so it means that it's not will be clean electricity inside the battery, right? So, but if you use solar or wind energies to charge your battery, of course, it will be also green energy inside. But you are absolutely right. So it's a fundamental limitation of lithium batteries. So you cannot achieve higher energy density in the battery. So, and what is energy density? Energy density is how long you can fly on your fly or drive your car or your air transport.
Okay, and I think that's a really important point because I know that perhaps maybe mainstream may be hearing of more electrification of mobility on the ground, but also in the aerial side. But the range and the energy density that you're talking about is critical. So let's get to the core of what you guys do, which is this turbo air cooled TPM hydrogen fuel cell system. Can you talk about the turbo air cooling architecture that's unique to what you guys are building?
So not only turbo air cooled, our unique approach in design and architecture of our fuel cells. So first of all, the HTPM, so it's a high temperature fuel cell, and because right now in 95% of fuel cell you can meet right now in the market, it will be low temperature fuel cell, and temperature of operation is about 70 degrees Celsius. And we are using high temp membrane, where the temperature of the chemical reaction is is about 160 degrees Celsius. So, and this high temperature of the chemical reaction, and the turbo air cool system, it's a new system architecture. So I would say this is where we efficiently utilize compressed air for both oxygen and cooling and oxygen supply. So we simply put, we increase pressure inside the fuel cell, deliver more oxygen in the electrochemical reaction. That allows us at the same time, on the one hand, to increase power output. At the same time, at the other hand, we can recirculate the air inside the fuel cell and dramatically decrease power consumption for turbocharger. So which provide you necessary pressure inside the fuel cell.
So again, I think what that means practically is that you're getting higher output, all the while actually making sure that your system is maintaining a certain, cooling temperature. And then, of course, the entire system, as a result of this design, means that it's lower weight compared to, let's say, traditional liquid cooling system. Is that
exactly? High temperature allows you to exclude commonly used liquid cool system. You can exclude also additional, subsystem around the fuel cell, like a humidifier, for instance, and etc. Because it's a high temperature, it means that any ambient air will cool the system. You can maintain very appropriate for electrochemical reaction delta T. It's a delta T. It means what's temperature differences between electrochemical reaction and ambient air. For low temperature fuel cell, where the electrochemical reaction is about 70 degrees Celsius, so it means that it's very, very difficult to maintain the temperature of the reaction in the very, very narrow range, because ambient air is very is higher. So it means that you cannot maintain very good delta T. So that is why you should add additional subsystem around the fuel cell, around the standard fuel cell, like a liquid cool, humidifier, and so on. So that is why they provide a lot of parasitic mass around the fuel cell. That is why specific power of low temperature fuel cell, specifically for air needs, it's very, very high, very, very low, because the system weight is very, very high.
So I think I think it's important to take a moment to recognize kind of the engineering I think advantage to what you're suggesting, is because all these subsystems or components that used to be surrounding the lower temperature types of fueling systems, all that weight and all those components have gone away, which means that the entire system becomes not only lighter but also less cost and less components, which means also less likely to break down as well. So there is higher reliability as well. Is that correct?
Exactly. So high temperature fuel cells allows our design. The system will be much simpler. And the main idea is that we also are going to use standard components. So that is why our plan is to build this full-scale system and deliver to our customers for the real flight in 2022. Because once again, we are going to use very simple design, standard components, and that is why the transition from single cell to full scale system will take only about 2 years.
Yeah, that's pretty incredible. So that's excellent. Again, I think you're referring to the next gen high temperature membrane, or HTPM. This is what you refer to. There's also another part that you guys focus on, which is a new catalyst and lightweight bipolar plate. Can you explain that a little bit more, please?
Yeah, so our company was founded in 2018. We started from the scratch and started developing the best in the class lightweight fuel cell system for drones and robots. So we designed everything. We designed our own bipolar plates, lightweight bipolar plates, and that system and catalyst recipes. And that system allows us to get all necessary knowledge and technologies how to build next generation hydrogen fuel cell system specifically for air transportation needs. So lightweight bipolar plates, we are really using very unique solution. We are the first company in the world who combined high temperature membrane with aluminum bipolar plates. It's our know-how, and also we are designing not only bipolar plates, but also highly conductive, anti-corrosion resistant materials. So, and because it directly influences on reliability of the system and the lifespan of the system. And regarding catalyst recipe, of course, so high temperature membrane historically integrated in stationary applications where it operates on low grade hydrogen. So that is why manufacturers usually, put a lot of platinum inside. And our idea is to design new type of catalyst specifically for high temperature membrane, where we will dramatically decrease the content of platinum in that catalyst. At the same time, we will keep the same performance, which is standard high temperature fuel cell use, because we're going to use it with purest hydrogen, like green hydrogen. It's very, very pure. And and this is our main idea.
Yes, I think there's a lot there to dig into. I mean, the fact that you're having to use less precious metal attributes to, everything from lowering costs, but also additional mining and the externality that comes from mining precious metals. The other thing that I think that's quite important is when we think about mobility in the air, is this notion of it just has to work, right? So, the last thing you want in an airplane or some sort of air vehicle is for it to stop working. So can you talk about, relative to more kind of legacy hydrogen fuel cell, how your system kind of compares relatively in terms of kind of longevity and just the ability to just make sure that it works?
So it's also that idea is also becomes from our system which we built for drones and robots. So it's a modular approach. So when we are talking about full scale system, it doesn't mean that we will build one system like a disassembled device. So our system divided to single models. It's, let's say 150 kilowatt system consists of 12 15 kilowatt models. So it's a 150 kilowatt, net power. So gross power 180 kilowatt system consists of 12 15 kilowatt models, and each model operates independently. It means that if something goes wrong with one of the model, it doesn't mean that all system will be shut down. So it will be more than enough to continue your flight procedure and etc. So this modular approach allows our customers to get necessary level of redundancy. It's the second point that our system, as I said earlier, it has very high specific power. It means that we can use that system as a primary source of energy. So we can exclude buffer battery and etc. So that is why it means that our system can cover all regions of operation of aircrafts: takeoff, cruise, landing, and etc. So if it means that, for instance, when you are in takeoff regime, you consume 600 kilowatts, it means that for a cruise mode, you will consume about 200 kilowatts. So 200 kilowatts, yes. So it means that we install you 600 kilowatt system, but actually 99% of operation of aircraft, you operate the system at lower level, so 200 kilowatts. At the same time, it also will provide you necessary level of redundancy, because your system working is a very, very, light regime.
Yeah, I think that makes a ton of sense. And I think, just making sure that you can actually plan, over design the potential energy use. And it's interesting that it actually serves as the main power source, but also as a backup in the case of, other battery systems or something else fails. And the point that you made,
our idea, sorry, Scott, our idea is to exclude buffer battery at all from the system design, because right now lithium batteries and other energy storage, it will be complicated to get certification in FAA. But
Well, I just to be clear, is that aren't there still battery components in a potential aviation craft that handles different sets? Let's say, for example, communication, right? So we're not talking about the power source for engine, but for
Yeah,
electronic systems, right?
yeah. So you can use right now lithium batteries for like a source energy for your devices, telecommunications, and etc. But it will be very, very complicated to certify that system for engines.
And then the
And
other point that I think really is critical is because of the modularity of the way the fuel cells work, is that it has a kind of a built-in redundancy. So even if a single cell failed, you have others that are running independently. And I think that's a really interesting and a very important point, especially again when it comes to safety, because I think it's all about safety and power. Let's talk a little bit about applications. There are many different types of applications, whether we're talking about aviation, air mobility, in the sense of drones, air taxis, electrical, vertical takeoff
Mhm.
types of vehicles, and fixed-wing airplanes. All of those have very different requirements. How do you fit within their specific schematics and their requirements?
So you're absolutely right. Our system will address to different market segments, starting from logistic drones, air taxis, eVTOLs, and different types of fixed-wing plane, turboprops and turbofans. So, and you're absolutely right. Depends on the market. It requires different approach for integration our system in that type of aircrafts. And in our team, we have all necessary expertise. So we hired system integration engineer lead who helps who has necessary expertise and experience, and he helped us to do so. So so before we starts our company, we started to think about how we will integrate our system in different aircraft, because we are electrochemists, chemists, physics, but not aircraft designers. So that is why we are hired and invited advisors and like a full-time employee in the company who helps us to do so.
Gotcha. Makes sense. And I think you mentioned that, was it the target of 2022 when some of this will be in production?
Yeah, so in 2022, it will be first deliver a full-scale system for the real flight based on our development agreement with one of our customers. So, but serial manufacture is going to be started from 2023, and we have pre-orders from that customer. So we are right now discussing him with in February of 2021. We're discussing with him 200 systems of 600 kilowatts power level.
Sounds great. So with that, I've been joined by Dr. Alex Ivanko, who is the CEO of HyPoint. Thank you for joining today.
Thank you.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.